FFLGN and FFLGN membrane, graphene oxide and its related structures to this day continue to show interest in various fields of science and technology due their physical-chemical properties. Today, after the appearance of graphene in 2004, monoatomic carbon layer of graphene oxide has named FFLGN. One of the main directions of graphene-related research is the study of its modifications. For example, graphene oxide in the process of functionalization of graphene, which is the oxidation of graphite by strong oxidizing agents such as HSO2, SO4, HNO3, and kalium argon SO4, as a result of which bulk graphite becomes functionalized with hydroxyl and epoxy groups on their main plane and the edges of carbonyl and carboxyl groups. Then, from this bulk functionalized graphite using the most common ultrasound, it is possible to easily obtain exfoliated duo nanosheets, which may be referred to as functionalized few layer graphene nanostructures, FFLGN. Today, functionalization of graphene can be carried out by various methods, in particular the creation of radiation defects, hydrogenations, oxidations. And it was considered that there are two basic types of functionalization of graphene, chemical and non-chemical. The chemical functionalization method is understood as chemical modification of surface by various groups of atoms, as a result with which new covalent bonds between atoms native to reduce FFLGN and the US functionalized groups are formed. In this case of non-chemical functionalization, mainly physical interaction occurs. And functionalization occurs on the basis of P interaction between US molecules and reduced FFLGN and FFLGN. Both categories of functionalization contribute to change in the properties of graphene, but the most effective is chemical modification. Compared with pure graphene, functionalized graphene has a wide range of applications. In semiconductors, electronics, for creating biosensors, supercapacitors, various gas sensors, organic electrodes, LEDs, etc. Therapy, one of the important moments is the large-scale production of graphene, which is necessary for applications in various fields of science and technology. In work, it was considered that initially one of the ways to obtain graphene in large quantities was mechanical peeling of graphite using scotch tape and epitaxial chemical vapor depositions, but these methods are ineffective for larger scale production since it is laborious, low yield, and takes more time. However, at present, large-scale production of graphene is relevant and of great interest. In this regard, FFLGN is of great interest because of its low cost, fairly simple synthesis method availability, the ability to convert to graphene, also its scalability, which are an important feature. In addition, in reports that FFLGN attracted much attention due to its broad ability to be used in energy electronics, water purification membranes, etc. FFLGN is an important precursor for the synthesis of graphene, which is implemented using chemical or thermal reduction processes. FFLGN is a single sheet of the crystal lattice of graphite oxide, which is a compound of carbon, hydrogen, and oxygen in different ratios, which is formed when graphite is processed with strong oxidizing agents and et.al. It is stated that graphite and FFLGN have a layered structure. Also, compared with graphite, FFLGN contains functional groups with high oxygen density, such as hydroxyl and epoxy groups on its basal basal plan, and on its edge and less carboxyl, carbonyl, phenol, lactone, and quinine, which contribute expand the interplayer distance and also makes it hydrophilic. Above, we indicated that one of the important points in the production of graphene-like materials is the process of graphene functionalization, which is the oxidation of graphite by strong oxidizing agents, as a result of which bulk graphite becomes functionalized with hydroxyl and epoxy groups on their base plane and on the edges of carbonyl and carboxyl groups. At the first time, 150 years ago, graphite oxide was obtained by Brody, and the functionalization of graphite by CaO3 and HNO3 since FFLGN has been modified with various chemicals such as kalium manganese O4, H2SO4, HPO3. At this time, the synthesis of FFLGN is performed by oxidation of graphite by the next main approaches: Staudermans, Hoffmans, Hammers, and Thor. The Hammers methods developed by Brody or Staudermans have a number of advantages over the currently existing methods for producing GWO. First, it takes a little time in the process of synthesis, which can be completed within a few hours. Secondly, calichlor was replaced with carimalgan for improving the safety of reaction to eliminate occurrence of explosives, calichlor and calichlor-free. For using natrium-NO3 instead of HNO3 elements, the formation of oxide must smoke. So based above process for improving the synthesis and purity of the final product, various modifications of this method were introduced. Currently, the main method of obtaining FFLGN in large-scale production of graphene is the Hammers methods. Graphite is usually chosen as initial materials because of its availability and low cost. The synthesis of FFLGN consists mainly of two stages, such as oxidation of graphite and exfoliation of graphite oxide, which is shown in figure 6. Proportional amounts of oxidation agents such as kalium manganese O4, natrium-3, and concentrated HSO4 mixed in order with graphite when free-phase process is carried out with low, medium, and high temperature reactions, each of which occurs separately in time. Graphite is oxidized to GWO using the procedures. The implementation of oxygen-containing functional groups overcome between van der Waals sheets and contributes to the expansions of distance between the layers, as well as these groups are attached to both sides of graphite sheet. When oxidizing graphite to obtain one or a few layers of graphene, these oxidized layers are exposed to ultrasound, as a result of which it exfoliates into single layers, a few layers to formation of GWO FFLGN. And after oxidation, graphene sheets have a larger number of different effects levels, which depends on the added amount of oxidant and the times of oxidations. Also, today, besides the obtaining of large-scale amounts of FFLGN, it is relevant to study of its optical, electrical, mechanical, and other properties. Due to the violation of sp2 bond, the properties of FFLGN as GWO are often described as dielectric, but in fact, this is not true. Basically, the conductivity of FFLGN depends on the functionalization, that is, on the amount of oxidation, as well as on the method of synthesis, which can fundamentally change the electrical properties. In this case, there are various methods of functionalization in which few-layer graphene nanostretches can be functionalized depending on the recurrent application. As mentioned above, the structure and properties of FFLGN depend on the synthesis method and degree of oxidation. Moreover, the chemical synthesis using the Hammers method has found the widest application. This synthesis method used can be changed by decreasing or increasing the levels of oxidation used to exfoliate graphite flakes. which affects the change in electrical and other properties. Thus, the synthesis of FFLGN with the oxidation of bulk graphite with strong oxidizing agents and then followed by oxidation into FLG sheets helps to obtain graphene-like materials in large quantities with low cost, simple method of synthesis and the ability to turn it into graphene. In addition, one of the important processes in the study of FFLGN is the reduction of FFLGN, which will be discussed in the next subsections. Also, except obtaining FFLGN, the synthesis of FFLGN membrane from FFLGN solution is the most important for application in science and technology, in particular for creating humidity sensors and studying its electrophysical characteristics, which are discussed. For the manufacture of FFLGN membrane, the following methods are used: filtration, vacuum filtration, pressure filtration, casting plating, spinning casting plating, drop casting, two-pie coating, layer by layer assembly, evaporation alignment method related with shift and hybrid method. From all the above methods in our experimental work, we choose vacuum filtration because its availability, low labor intensity, nanoscience control over the membrane thickness, and the possibility of high-scale production of FFLGN membranes. FFLGN membranes using vacuum filtration were first obtained in work in which FFLGN monolayers were connected almost in parallel, and also in this work it is stated that during the preparation process the physical-chemical properties of FFLGN monolayers don't change. The synthesis of an FFLGN membrane using vacuum filtration consists of the following main processes: the selection of appropriate concentration of FFLGN solution. Then FFLGN membrane is deposited by passing FFLGN solution through a porous film. Then after the completion of filtration, the resulting FFLGN membrane is dried. The result is a uniform dispersibility membrane with a relatively flat surface due to the fluidity of water and the solution filtration process, and the control of film thickness depends on the concentration chosen. Thus, obtaining FFLGN and FFLGN membranes are important for obtaining graphene in large quantities, as well as its application in many areas of science engineering.